y is also going to positive infinity and ends in quadrant 1. And that's just basic stuff. I'll do cubic as well. So cubic, same thing. Domain and range. Domain is just all x values, so xer or negative infinity to positive infinity. And range, in this case, this function does go all the way down and it goes all the way up. So range is also all real numbers, or from negative infinity to positive infinity. As for the end behavior, when x is getting really small, so start from the origin and go to the left. What's happening to my function? It's going down, 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 down. So y is going to negative infinity, or it's also starting in quadrant 3. I should say and. As x goes to positive infinity, so from the origin, x is getting bigger and bigger and bigger. What's happening to my y values? Well, they're going up, 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 up. So y is going to positive infinity, and the function is ending in quadrant 1. So I'm not going to go over every single one of them in detail. These notes have been posted. These solutions have been posted for you, so you can definitely take a look at that. All right. What else? Key features and even degree power functions. So we talked about end behavior, and this is for even degrees. So for even degrees, you'll notice that the end behavior is almost always y is going to positive infinity always. It's always like this. It all depends on the leading coefficient, though. So we'll talk about that because sometimes it could be reflected and just flipping down. But essentially, the end behaviors are when the leading coefficient is positive, y is going to positive infinity. When leading coefficient is negative, then y is going to negative infinity both times. Domain is always xer, and range is either bigger, the function is above 0, 0 and bigger, or 0 and smaller, depending on if it's reflected up or down. And these are examples of even functions, even degree power functions, even degree power functions. Okay, something new, line symmetry. Line symmetry is a graph that has a line of symmetry if there is a vertical line, x equals a, that divides the graph into two parts, such that each part is a reflection of the other. So the graphs of even degree power functions have line symmetry about vertical line, x equals 0, the y-axis. So even degree functions may have line symmetry. So if you can cut it in half and fold it over and it kind of overlaps, then that's line symmetry. Odd degree power functions. So odd degree power functions, you'll notice a pattern in that the end behaviors are opposites, meaning if it's starting from quadrant 3, it's not going to end down in the negative infinity again. It's going to go to the opposite end. So as x is getting smaller and smaller and smaller in this example, y is also getting smaller and smaller. So as x goes to negative infinity, y goes to negative infinity. But as x gets bigger, then y is also getting bigger. So as x goes to infinity, y goes to positive infinity as well. So that is when your leading coefficient is positive. But if my leading coefficient is negative, it's reflected. So that means that when x is going to negative infinity, when x is getting smaller and smaller and smaller, y is actually getting bigger and bigger and bigger. It's going to positive infinity. And when x is going to positive infinity, it's getting bigger and bigger. Y is getting smaller and smaller, so y is going to negative infinity. So just be careful. The leading coefficient really affects your end behaviors. That's kind of one key takeaway. The other thing you should know is that for odd functions, for odd degree power functions, usually they have opposite ends. For even degree power functions, they usually have the same end behavior. All right, point symmetry. What is point symmetry? So point symmetry is a graph has point symmetry about point A, comma B, if each part of the graph on one side of AB can be rotated 180 degrees to coincide with part of the graph on the other side of AB. So if I were to rotate this whole graph 180 degrees, I know it's hard to see. Actually, hold on. I just realized I can show you. So this is my graph. If I rotate 180 degrees, it's exactly the same graph, right? Like you see that's what point symmetry is. So see here, this is the original graph. You can see A and B are the right way up. And then when I rotate 180 degrees, so this is 90 and this is 180. And now it looks exactly the same as the original graph. If you don't believe me here, I'll just clone it. And there. See, it looks exactly the same. One is upside down, one is right way up. So that is called point symmetry. If I can rotate the graph 180 degrees about at 1 point, then it's yeah, that has point symmetry. Okay. All right. What is this? Right each function. Right each function. Oh, okay. Hold on. Let's see if we can figure this out. Excuse me. All right. So here we have an example of NB. Here, let me copy this. Okay, so everyone should know quadrants 1, 2, 3, and 4. That's just common sense. So end behavior is quadrant 3, meaning it starts from quadrant 3 and it's going to quadrant 1. So this is kind of what's happening. I kind of supposed to go through the origin, but it doesn't matter. All right, so what functions do that? Well, we know that odd functions have opposite end behavior. So it has to be an odd function. So it has to be an odd degree. So it could be y equals 2x. That's a possibility. Can it be any other numbers? Well, yeah. Can it be negative 4x to the power of 5? And if it was y equals 4x to the power of 5, I would say yes, it's possible. But not negative 4x to the power of 5. Why? Because that negative value actually swaps the end behaviors, because that leading coefficient. So I doubt it's that one. It can't be any of the even ones, because remember, it's even degree functions have the same end behavior. So it could be y equals x to the 7. Yeah, I don't see a reason why it can't be that one. And I don't think it's going to be this one, because once again, the leading coefficient is negative. So I'm going to write these two as my answer for quadrant 3 to 1. What about quadrant 2 to 4? Well, quadrant 2 is here, and quadrant 4 is here. So, so it's actually, once again, going in opposite directions. So yeah, like one's going up, one's going down. So it's going to be an odd value again. And in this case, though, it's starting kind of, in this negative section and then going here. So that leads me to believe that it's going to be an odd degree function with a negative leading coefficient. So probably y equals negative 2 over 5 x to the 9. And then y equals negative 4x to the power of 5. And I think that's it, because the rest are all even, and the other two we already used. Okay. Moving on. What about 2 to 1? So 2 is here, and 1 is here. So that definitely looks like a even, parabola, like y equals x squared. So just an even function. So y equals x to the 10. Probably what other even functions do we have? We have x to the 8, but remember, there's a negative leading coefficient here. So this doesn't look like y equals x squared. Sorry, what I mean is y equals negative 0.5 x to the 8. Doesn't look like y equals x squared, because it has a negative leading coefficient. And this is also negative leading coefficient, negative leading coefficient. This is odd. This is odd. So the only one left is 5 times x to the power of 6. All right, so those are the two. And then the last two remaining is from 3 to 4. So 3 is here, 4 is here. So once again, even functions, but this time negative leading coefficients. So y equals negative 0.5 x to the 8. And what's the other negative one? And y equals negative 3x squared. And let's see if we did it right. The answers are somewhere here. Yeah, and you can check we did it right. odd exponent, negative leading coefficient. Oh, let's see what's happening here. For each of the following functions, state domain and range, describe end behavior, identify any symmetry. Yeah, I'm just going to quickly go over this. So this is an odd degree function. So in this case, domain is XER and range is YER, or in this case, if you're doing bracket notation, or forget what it's called. But yeah, this type of way, use round brackets. And as x goes to negative infinity, y is going to positive infinity. As x goes to positive infinity, y is going to negative infinity. So these are your end behaviors, and it has point symmetry about the origin. Because if I were to take that point and rotate it, it will be the exact same function. So that's called point symmetry. And remember, if it's an odd degree power function, then yeah, it has point symmetry. And this is y equals negative x. All right, this is y equals 0.5 x squared. This has domain and range. Range is obviously only above the 0 point. And we've done end behaviors and domain and range for this. This has line symmetry. So yeah, this is pretty straightforward. This is odd. So if it's odd, we know that it has point symmetry, and the end behaviors you can clearly see is from quadrant 3 to 1, and domain and range is all the real numbers. Okay, so that's it for this lesson. I wanted to go over the second lesson now, which I have yet to post, which I'll be posting basically right now once we get off the call. And that is one moment as I find it. Where it is. Okay, this is it. So lesson 2, characteristics of polynomial functions. Now remember, my lessons are not 100% coinciding with the course's lessons. They do overlap quite a bit, but it may not be 100% in order. So just understand that. So here we have characteristics of polynomial functions, new terminology, local min, max, absolute max min. So in this example here, this graph, we know that this function goes all the way up and all the way down, meaning it has a range of all the real numbers and it has a domain of all the real numbers. But there's something happening in the middle of this graph. There are some kind of like humps and like valleys, you could say, like drips and stuff. So what happens here is these are called local minimum or local maximum points. So in this graph, -1, 4, this point here will be a local maximum. All right, local max. And this value here, 1, -4, that would be considered a local minimum because it's a minimum value. I know a lot of you have to go to your next class. That's fine. You can go ahead and you can just watch the recording. Okay. Thank you for showing up. So these are not absolute minimum and maximum points because there are other points on the graph of the function that are smaller and greater. Sometimes local min and max points are called, this is important, turning points. And here, I'll share this with you so you guys can see. So local max, local min, and turning points. In this graph here, in this example, what's happening? We have 2 local minimums and 1 local maximum. So there are 3 local minimum / maximum points, 3 in total, including all maximums and minimums. And 2 of them are local minimums, and 1 is a local maximum. And one of the local minimum is an absolute minimum, and it is labeled. Why is this considered an absolute minimum? Because the graph does not go below that point. So an absolute minimum can also be considered a local minimum. So don't confuse the two. But yes, that's very important. So a few things once again, recap: turning points, local min, local max. You guys should know that. The degree of the leading coefficient in the equation of a polynomial function indicate the end behaviors of the graph. The degree of a polynomial function